We're tracking an unusual situation tonight in Yellowstone National Park. Large numbers of animals appear to be migrating south.
Yellowstone's valleys have been emptying fast. Elk, bison, deer, and even smaller animals are leaving in massive groups, heading for higher ground as if they're escaping from something.
Hundreds of mountain lions have been leaving Yellowstone National Park, headed south to Salt Lake City, Utah.
Tourists are filming it, and scientists are scrambling for answers, because this isn't just any park. It sits on one of the most powerful supervolcanoes on Earth, a giant that could wake without warning. Is it simply migration, or the start of something we're not ready for? Let's find out. The truth about Yellowstone's animal escape. In July of 2025, Yellowstone National Park became the center of a mystery you could watch unfold in real time. Elk, bison, deer, and smaller animals began leaving the valleys in large groups, heading toward higher ground. Visitors filmed it, researchers documented it, and the videos spread quickly online. People everywhere began asking the same thing. Why were thousands of animals suddenly leaving Yellowstone? The concern wasn't just about the migration itself. Yellowstone sits on one of the largest active volcanic systems in the world. It hasn't erupted in thousands of years, but the same underground heat that powers its geysers and hot springs also fuels constant change beneath the surface. That's why big animal movements here make people pay attention. When wildlife shifts in large numbers, some wonder if nature is warning us before something bigger happens. Recent months had already brought an increase in small earthquakes and subtle ground changes. None were serious enough to trigger official alerts, but enough to catch scientists' eyes. Some biologists believe the shaking nudged animals away from usual feeding grounds, pushing them to cooler, safer areas. Others think they might be sensing changes humans can't, like tiny vibrations, trace gases, or small temperature shifts. Officials told the public there was no reason to panic, but they still launched close monitoring. Teams of biologists, geologists, and rangers began tracking where the animals were going, how fast, and in what numbers, hoping to pinpoint what had changed. Soon, something else caught people's attention, a slow-growing bulge under part of the park. Regular watchers of Yellowstone's live cameras claimed they could see a dome-shaped rise that had been forming for months. They compared older and newer images and said it looked more obvious now. One theory was that magma deep underground was pushing the surface upward, something that can happen before volcanic eruptions. Another idea was that the park's hot water system was building pressure, which can also push the ground upward. But because the shape stayed so steady, many thought magma movement was the more likely cause. That's the fear nobody likes to say out loud. If magma is pooling, the risk of an eruption gets higher. It could be a small, local blast of ash and lava, or in the worst case, an event big enough to send ash high into the atmosphere, block sunlight, disrupt farming worldwide, and cool the planet for years. Even a smaller eruption could destroy wildlife habitats, damage towns, and overwhelm hospitals with breathing problems. Then came a burst of earthquakes. Tourists caught a blast near a hot spring that sent people running off a boardwalk. Biscuit Basin was shut down while geologists looked into it. Some people online claimed certain quakes weren't showing up on public records, and even pointed to a supposedly unreported magnitude 2.4 event. That sparked talk. Were officials hiding data to avoid panic, or was this just normal for such a geologically active place? A leading scientist calmed fears, explaining that the quakes were within Yellowstone's usual range. The park averages about 1,500 to 2,500 earthquakes each year, often 100 to 200 per month. The crust here is thin, heat is intense, faults are common, and groundwater is always moving. That combination creates many small quakes, most too weak to feel. Still, the unusual wildlife migration kept eyes on the park. Some animals are known to sense environmental changes before humans, things like shifts in electric fields or gas leaks. Yellowstone has also shown plenty of recent activity. In the last 2 years, it has displayed 2 of the 3 most common eruption warnings: increased earthquake activity and more surface gas vents. New erupting vents and surface cracks even closed part of a boardwalk in the upper geyser basin. None of this meant an eruption was certain, but it was enough to keep watch close. So how do scientists actually keep watch on a system this big? Over 50 seismometers detect earthquakes and movement underground. GPS stations, satellites, and borehole strain meters measure even the tiniest changes in the ground's shape. They also test water and gas from geysers and vents for changes in carbon dioxide, sulfur dioxide, and hydrogen sulfide, which can show what's happening below. Satellites scan for heat and emissions across the park. This data helps officials decide when to close areas, issue warnings, or prepare for emergencies. Recent studies have given scientists a better view of Yellowstone's underground system. Using seismic tomography, like a CT scan of the Earth, they found a huge lower crust reservoir of partially molten rock, big enough to fill the Grand Canyon many times. Above that is a smaller upper chamber, and deep below is a mantle plume, bringing heat from far inside the planet. Most of this rock is solid, with pockets of melted material, but knowing how heat and magma move helps improve eruption forecasts. Earthquake swarms have a long history here. Most are small and over quickly, and many go unfelt. Past swarms in the 1980s near Hebgen Lake and in 2008 near Yellowstone Lake gave scientists valuable data. These swarms are often caused by stretching crust, moving faults, shifting magma, or hot water carving new paths underground. While they rarely cause eruptions, visitors and locals are always advised to secure heavy objects, keep emergency supplies ready, and know how to stay safe during quakes. Strange animal movements aren't just random, they've been nature's alarm bell before. And in 1980, that bell rang loud around Mount St. Helens, just before it exploded. The day Mount St. Helens erupted. In the early spring of 1980, Mount St. Helens in Washington looked calm and harmless under its snow-covered peak. Elk grazed in open meadows, and the summit stood quietly against the sky. That peace ended on March 20th, when a magnitude 4.2 earthquake shook the mountain, breaking 123 years of silence. Just a week later, it sent out steam and ash for the first time in a century. From then on, the volcano stayed restless. Quakes rattled it daily. Steam bursts rose from the summit, and its slopes began to change in ways no one could miss. The biggest changes happened on the north side. Scientists used reflectors and lasers to track movement and saw the numbers spike. A bulge was growing outward at about 5 feet each day, and by mid-May, parts of it were over 450 feet taller than they had been the summer before. This was a clear sign that magma was forcing its way in, building dangerous pressure. From March to mid-May, there were about 10,000 earthquakes. Instruments also picked up steady vibrations that show fluids moving underground. As this went on, locals began noticing wildlife acting in ways that were far from normal for springtime in the area. Elk and deer, which usually stayed in certain high meadows during that season, were showing up in valleys and lowlands they normally avoided. In some cases, whole herds were grazing close to roads or moving through farmlands, something residents said they rarely saw. Bird activity also shifted. Certain groves that were usually filled with constant birdsong had gone strangely quiet, while other areas seemed to have unusually large flocks gathering together. People living near the mountain talked about hearing fewer woodpeckers and songbirds in the forested slopes closest to the crater, and instead seeing more of them farther away toward calmer ground. These were not official wildlife surveys, but they matched what scientists would expect when an animal's home range is shaken, blasted with steam, or filled with strange smells from volcanic gases. The changes suggested that the animals were instinctively moving away from the parts of the mountain that were becoming unstable, responding to things they could sense, like tremors, vibrations, or shifts in air quality, long before humans could measure them. At 8:32 on the morning of May 18th, a magnitude 5.1 earthquake struck beneath the bulge, and all hell broke loose. In seconds, the entire north side of the mountain gave way in the largest landslide ever recorded on Earth. That sudden collapse unleashed the massive pressure that had been building for weeks, and the volcano erupted sideways. A roaring blast of hot gas, ash, and rock tore north at hundreds of miles per hour, and within minutes, a towering ash cloud was climbing into the sky and beginning its journey across the country. The lateral blast destroyed about 230 square miles of forest. Trees near the crater were reduced to stumps, while those farther out were blown flat, all pointing away from the volcano. Lahars, fast-moving mud flows, tore down rivers, destroying bridges and filling channels with logs and debris. Towns downwind were plunged into darkness at midday as ash covered streets and rooftops. Wildlife in the blast zone stood no chance. Officials estimated nearly 7,000 large animals, elk, deer, and bears, were killed, along with most small mammals and all birds nearby. Fish hatcheries were wiped out, and wild fish faced blocked, debris-filled streams. Animals that had moved away before the eruption helped repopulate the area. Gophers, amphibians, and other creatures that survived underground or underwater helped restart the ecosystem when the ash cooled. The human toll was also heavy. 57 people died, many outside the strict closure zones because the sideways blast reached farther than expected. More than 185 miles of roads and 15 miles of rail lines were damaged or destroyed. The eruption also wiped out 4 billion board feet of timber. Damages were estimated at about $1.1 billion in 1980, and Congress approved $951 million in relief. Cities like Yakima spent weeks and millions of dollars clearing ash. The eruption left serious engineering challenges. Spirit Lake's outlet was buried, creating a flood risk. In 1985, engineers built a drainage tunnel through a nearby ridge and later constructed a sediment dam on the North Fork Toutle River. These, along with regular dredging, still protect communities downstream today. Recovery began surprisingly fast in sheltered spots. When the snow melted, green plants emerged. Lupines spread quickly, adding nutrients to the soil and helping other plants grow. Spiders arrived on silk threads, insects explored the new ground, and gophers mixed ash with richer soil. Elk and deer returned, feeding on the fresh growth. What had looked like a lifeless gray wasteland in 1980 showed green within a few summers, giving scientists a unique chance to study how life returns after total destruction. Mount St. Helens stayed active. Between late 1980 and 1986, a lava dome grew in the crater in several phases. In 2004, another dome began forming and grew for more than 3 years, splitting the crater's glacier before it joined again below. These smaller eruptions gave scientists valuable data on magma movement and allowed them to test new monitoring tools like GPS, advanced seismometers, and all-weather cameras. One clear lesson came from the animals. Instruments can track quakes, ground swelling, and gas changes, but wildlife often reacts in ways that confirm the danger. In 1980, animal movements matched the scientific data showing rising magma and pressure. Animals farther from the blast zone survived and helped bring life back. The disaster changed how volcanoes are monitored in the United States. The Cascades Volcano Observatory was created, and networks of sensors, GPS stations, cameras, and gas detectors now watch the region closely. Engineers maintain the flood control systems built after the eruption. Schools teach the science and history, and visitors can see the crater, lava domes, Spirit Lake's new shoreline, and the regrown forest. The mountain will erupt again someday, but thanks to 1980, we know the signs, we have plans, and we understand that listening to both instruments and animals can save lives. Mount St. Helens proved animals can sense danger long before we do, and in 1991, Mount Pinatubo showed it again. The full story of the Mount Pinatubo eruption. In the first months of 1991, Mount Pinatubo in the Philippines looked like nothing more than a peaceful green mountain. It sat quietly in the Zambales Range, surrounded by rice paddies that glistened in the sun. Children ran along the dikes, carabaos pulled wooden plows through the muddy fields, and villages went about their normal routines. There was no sign that this quiet mountain was about to become the center of one of the biggest volcanic eruptions of the 20th century. That all changed on April 2nd. Without warning, steam and ash suddenly burst from vents on the volcano's northern slope. Scientists from PHIVOLCS, the Philippine Institute of Volcanology and Seismology, rushed in to investigate. They quickly set up a seismograph to measure earthquakes and began monitoring the activity. Within weeks, the U.S. Geological Survey arrived at nearby Clark Air Base with more equipment to strengthen the monitoring. Together, they built a full network, 7 seismometers to detect and send quake data by radio, 2 tilt meters to measure swelling in the ground, and a COSPEC device to track sulfur dioxide gas coming from the volcano. While the scientists worked, people in the surrounding villages noticed strange changes. Farmers said their carabaos, which normally walked straight into flooded rice paddies without hesitation, were refusing to enter and instead pulling toward dry ground, or even uphill. Birdwatchers saw fewer birds in areas near the volcano, while unusually large flocks gathered farther away in the valleys. These weren't official studies, but they matched what scientists were picking up: more steam, more rumbling, and more shaking beneath the surface. Animals seemed to sense the danger before the instruments could fully explain it. By the middle of May, the data confirmed that something serious was brewing. The first sulfur dioxide readings showed about 500 tons per day coming from the summit vents. That was already a sign that magma was rising underground. But just days later, the number shot up to more than 5,000 tons per day, a 10-fold jump, showing that magma was much closer to the surface. Then, just as quickly, the readings dropped to only a few hundred tons. This was not a good sign. It likely meant that the gas escape routes were sealing shut, trapping pressure inside the volcano. At the same time, swarms of earthquakes rattled the upper slopes, and tilt meters recorded steady swelling as magma forced its way upward. The first eruption came late on June 7th. An explosion sent a towering column of ash nearly 5 miles into the air. By the next morning, a new lava dome had formed near the summit vents. The alert level was raised, and the evacuation zone was expanded. On June 10th, the U.S. military began moving about 15,000 people from Clark Air Base to Subic Bay. By June 12th, after another massive ash column rose more than 12 miles high, the danger zone was extended to 19 miles, and the number of evacuees climbed past 58,000. Many Ida families who lived on the volcano's slopes had already started leaving, carrying what they could on foot. Then came June 15th, the day the world would remember. Highly gas-charged magma finally reached the surface. The eruption was explosive beyond anything most people had ever seen. A gigantic mushroom-shaped cloud blasted into the stratosphere, climbing to about 22 miles high. Deadly pyroclastic flows, scorching avalanches of ash, gas, and rock, poured down every side of the volcano at incredible speed, filling deep valleys with deposits tens of meters thick. As if that wasn't bad enough, Typhoon Yunya passed directly over the region at the same time. The heavy rain mixed with the falling ash, creating a thick, heavy sludge that piled up on rooftops. Thousands of buildings collapsed under the weight. Fine ash spread across nearly the entire island of Luzon, turning day into night, and satellites tracked the ash cloud as it circled the globe. The destruction was staggering. More than 300 people died during the eruption, most from roof collapses made worse by the typhoon rains. When later deaths from disease and displacement were counted, the toll climbed to over 800. Roads, bridges, and irrigation systems were destroyed. Ash damage shut down airports, grounded planes, and damaged 17 commercial jets, costing around $100 million. The only reason the death toll wasn't in the thousands was because of the early warnings and massive evacuations organized by FIVOLCS and the USGS. Animals faced the same life or death divide based on location. Those close to the vents or caught in the pyroclastic flows stood no chance. But many farm animals survived because families left early, bringing their carabaos, pigs, chickens, and goats with them. Wild animals slowly returned, starting at the edges of the new ash deposits. Years later, scientists found small mammals thriving in the recovering forests, proof that life comes back quickly once the land cools and plants begin to grow again. The eruption didn't just affect the Philippines, it changed the planet's climate. Satellite studies showed that Mount Pinatubo had blasted between 17 and 20 million tons of sulfur dioxide into the stratosphere. This gas formed a layer of sulfate aerosols that reflected sunlight, cooling the Earth by about ½ degree Celsius for nearly 2 years. Pinatubo became the modern example of how one eruption can impact the entire world. But the danger didn't end when the volcano quieted. The thick, loose volcanic deposits in the valleys stayed in place, and when typhoon or monsoon rains arrived, they turned into lahars, giant, fast-moving rivers of mud and ash that roared downriver and destroyed homes and farmland over and over again. These lahars caused more long-term damage than the eruption itself. Engineers built dikes, rerouted rivers, and raised roads, but seasonal rains kept triggering more lahars for years. Even with all the destruction, there were clear successes. Experts estimate that at least 5,000 lives and $250 million in property were saved because of accurate forecasts and timely evacuations. Around 200,000 people in the lowlands were evacuated, and 20,000 Ida Highlanders were permanently resettled from the dangerous slopes. The way Pinatubo was monitored and managed became a model for volcano preparedness around the world. The reason the scientists got it right is because they didn't wait for one single perfect sign. They looked at the whole picture. Gas readings shot up from 500 to over 5,000 tons per day, then dropped sharply, showing the system was sealing. Earthquake swarms became more frequent and shallower. Tilt meters showed the ground swelling. A lava dome appeared. Ash plumes grew taller with each event. All the evidence pointed to an eruption, and that's why evacuations happened in time. Today, the landscape tells the story. A deep blue lake now fills the giant crater where the summit used to be. Wide, pale riverbeds cut through the ash-filled valleys. Farms have returned to higher ground, and children once again guide carabaos through the fields. Birds have filled the wetlands and hedgerows, and small mammals thrive in the young forests that have grown on the fresh volcanic soil. Pinatubo showed that listening to animal warnings can save lives, but in Colombia, years earlier, those same signs were ignored, and thousands of people paid the price. The deadly 1985 eruption of Nevado del Ruiz. In November of 1985, the Colombian town of Armero sat quietly in the valley below Nevado del Ruiz, a snow-covered volcano in the Andes. Life in the valley felt normal. Cattle grazed along the rivers, horses wandered near the fences, and farm dogs lay in the yards. High above, the mountain's white ice cap glistened under the afternoon clouds. But for weeks, the people who lived there had been noticing small changes. Herds were leaving the low, wet pastures earlier in the day, preferring the firmer ground farther upslope. Some horses refused to drink from streams that now smelled faintly of sulfur. Dogs barked more at night and startled at tiny tremors that barely made water ripple in a bucket. These weren't official reports, just observations passed from neighbor to neighbor, but they matched what scientists had been recording since late summer. The mountain was stirring. By September, Nevado del Ruiz was back on Colombia's hazard watch lists. Small puffs of ash and bursts of volcanic gas were rising from the summit. Seismologists logged swarms of small earthquakes, not one big quake, but a constant background rattle. Geologists warned about one specific danger that made Ruiz especially deadly: ice. The summit's ice cap covered miles of the volcano. If hot volcanic flows reached that ice, the meltwater could rush down the mountain, pick up ash and debris, and turn into massive mudflows called lahars. Those lahars could tear down the steep canyons straight into the towns and farmland below. In the weeks before the disaster, the warning signs grew. Fumaroles, volcanic steam vents, hissed more loudly. Fresh yellow sulfur stains appeared on the rocks around the crater. Light ash fell on towns miles from the summit, carried by the wind. The few seismic instruments in place picked up steady shaking beneath the cone. Gas sampling detected sulfur dioxide, a clear sign that magma was rising. Not just harmless steam. No single sign could guarantee a big eruption, but together, the pattern was obvious to volcanologists. The system was moving toward danger. November 13th began like any other rainy season day. By afternoon, light ash was falling in some areas, but by evening, it had stopped. Many in the valleys assumed the danger had passed, but after dark, hidden by rain and cloud, the summit finally broke. At about 9:09 p.m., an explosive pulse blasted hot pyroclastic surges, fast, searing clouds of gas, ash, and pumice, across the summit ice cap. The ice didn't melt slowly. The heat from the surges melted huge amounts of snow and ice within minutes. Water poured into deep gullies and river channels, mixing with ash, boulders, and soil to form powerful lahars. Several of these mudflows formed almost instantly and began racing down the mountain. The largest followed the Lagunillas River toward Armero, a town of roughly 29,000 people built on old lahar deposits. In the valleys below, there was no way to see what was coming. Power failures knocked out communications. The rain muffled the distant roar. By the time anyone realized what was happening, it was too late. Around 11:30 p.m., the front of the Lagunillas lahar slammed into Armero. In minutes, entire blocks of the town disappeared under a thick, cement-like mass. Survivors described hearing a deep rumble, then complete darkness, then the cold, crushing mud sweeping away homes, cars, animals, everything in its path. By morning, one of Colombia's worst disasters was revealed. More than 23,000 people were dead in Armero alone. Hundreds more were killed or injured in other towns and villages west of the volcano. For animals, as for people, survival came down to location. Livestock left in the river bottoms, the easiest grazing land, were taken instantly. Cattle tethered near the banks were swept away with barns and fences, but animals that had been moved upslope or had wandered away from the rivers in the days before survived. Farmers later recalled cows and horses refusing to settle in the low meadows, and dogs pacing restlessly in the nights before the eruption. Those accounts line up with the physics. Lahars stay low in the valleys. Even a short climb to higher ground can mean the difference between life and death. The tragedy was made worse by the fact that experts had already identified Armero's risk. Months earlier, hazard maps clearly showed the lahar paths, and those maps put Armero directly in harm's way. But hazard mapping is only useful if the warning reaches the people who need it, and on that rainy night, communication failed. Some residents were told the ashfall was not dangerous and went to bed. The lahars took more than 2 hours to reach the town. That was enough time to walk to. Safety, if people had known the real danger. In the days after, scientists studied the deposits to piece together the exact sequence. Pyroclastic flows had crossed about 10 square kilometers of summit ice, melting an enormous volume of water almost instantly. As the lahars charged downhill, they picked up clay-rich soils that made them thicker and more cement-like. The flows split and rejoined in the valleys, spreading across wide floodplains and leaving deep layers of mud where towns had stood. The physical disaster was only the beginning. Every rainy season for years afterward brought new lahars. The fresh volcanic deposits in the canyons were loose and unstable, and heavy rain turned them into more floods of mud and debris. Crews built dikes, raised roads, and dredged channels over and over. Farmers who had saved their animals still needed new grazing land far from the dangerous riverbeds. Entire communities had to relocate schools, clinics, and homes to higher ground. In the middle of all this, Colombia and the world began making changes. Volcano monitoring networks expanded, communication plans were redesigned, so warnings could be sent directly from scientists to the public without delay. The U.S. and its partners created the Volcano Disaster Assistance Program specifically because of Armero, so experienced teams could respond quickly anywhere in the world. In Colombia, scientists at what is now the SGC improved monitoring of Nevado del Ruiz and other volcanoes, and they launched public education programs to explain in plain words what lahars are and where to go when the mountain starts to change. Even with all these improvements, the danger remains. Nevado del Ruiz still has a large ice cap. The valleys below are still home to thousands of people. History shows that smaller eruptions, like those in 1595 and 1845, also melted enough ice to send deadly floods down the slopes. Today, modern seismometers, gas sensors, and cameras watch the mountain constantly, but drills and simple direct messages about evacuation routes are still essential. A hazard map on a wall can only save lives if it gets people moving when it matters. And there is one detail from 1985 that should never be forgotten: the animals. In farm country, people notice when cows won't graze where they usually do, when a horse pulls away from a familiar water source, or when dogs pace and bark through the night. Those signs may not be exact science, but they are often early warnings. In 1985, those animal behaviors matched the instruments, the ashfall, and the gas readings. The mountain was already sending signals, and some of the simplest warnings were walking on 4 legs. Thanks for watching. See you in our next video.